Can a magnetic field make a coil spin? And the answer is yes, because that's the core idea behind every electric motor. In this video, I'll teach you how a loop of current experiences torque, how it creates rotation, and we'll go through some math formulas. Let me give you a visual, but it's a pretty weird looking one, so I'll draw it out first. What is this? This is a rectangular loop of wire inside of a magnetic field. The magnetic field is pointing to the right, and it's constant and uniform. The current flowing through this wire is clockwise, so it comes in here, around and out here. And since it's clockwise, the top path, which is this way, is parallel to the magnetic field. Same with this bottom section is parallel. So there's no force that gets created. But here and here, it's perpendicular. So yes, there is a force. Only the vertical wires matter here because the magnetic field B is horizontal and force only happens when the current is perpendicular to B. You can find where the force points with the right hand rule. Let's do it for the left side first. The current's coming up this way. So that's where your fingers would point. And then you would bend your fingers to the right because that's where the current's going. And then where does your thumb go? Your thumb is going into the screen. It's going in, like away from you, forward. For this side, if you did it, the current is coming out toward you. It's coming out of the screen, out of the page. And these are the symbols that you'll see for that on things like textbooks and exams. And what's the effect? You now have equal and opposite forces on the left and right side. They're pushing the loop, so the left side is pushing it into the screen, and this side here is pushing it out of the screen. Can you imagine that? This setup, if we look at it from a bird's eye view, so like if you're up here and you're looking down at it straight down, it looks something like this being the wires. It would start to spin like that. This setup has created a torque and it rotates our loop because one side's getting pushed forward or in, one side's getting pushed out, so it spins. Why do the top and the bottom do nothing? Of course, it's because it's parallel to the magnetic field, remember? Force is zero. So this is the idea of how the magnetic field and magnetic force can create torque. So here's the formula that we're going to derive. And I'll shove it up in the corner so that we can keep our eyes on what we're trying to do. And I'll show you how to derive it. So first, the force on each side of our little contraption from earlier is given with this formula, which we've seen before. And of course, all of these formulas are on the free cheat sheet in the description. And the two sides, remember these sides, let's say it's a distance B between them, how far they are apart. So if you remember back to rotational dynamics, the torque formula was force times the lever arm. The lever arm for our spinny situation here, it's the distance like that. So there's 2, B over 2 times 2, or just B. That means the total torque is the force, so ILB, multiplied by the lever arm, B over 2. And then you multiply this by 2 because there's two sides doing the spinning. Here's the thing. Length times B is area. So we can simplify this, compact it into one formula. Torque equals I times B, the magnetic field, times area. And because we multiply it by 2, that cancels out. This is the torque for one loop. And if you want to add more loops, let's say there's an n number of loops, then your formula is this. N, I, B, A, like that, taken from here, multiplied by sine of the angle between the coil's face and the magnetic field B. Formula derivations are always very math heavy, so it's okay if you didn't fully follow that. It's just to show that this formula doesn't come out of nowhere. And understanding formulas helps build your intuition. I've wrote here M equals NIA. This is called the magnetic dipole moment. So dipoles, if you remember, were those special electron configurations. Remember our torque formula that we just found? NIAB sine. NIA is M. So the final torque formula is MB sine. All of these are on the free cheat sheet in the description. And it behaves just like an electric dipole in an electric field. The torque will try to rotate your loop to align with the field. So when the angle is 0, there's no torque. When the angle is 90 degrees, there's going to be maximum torque. So if you look at that example from earlier with our rectangular thing, and we're looking at it from top down, and we started spinning, the angle with the magnetic field, it would be trying to align it. So it creates torque. Let's go through an example problem to make some sense of this. Say you have a circular coil with a diameter 0.3 meters, which means the radius is 0.15 meters. The current going through is 4 amps. Magnetic field is 1.5 teslas, and the number of loops in our coil is 12. What is the maximum torque? First of all, we have to find the area because our formula involves area. The area is pi r squared for a circle, which gives us 0.0707 meters squared. The magnetic moment is NIA, which is N12, I, which is 4, and A, which we just found, giving us 3.39, and the unit is amps per meter squared. Great, we have M. Max torque is found with MB, which is the moment, 3.39, multiplied by the magnetic field, which is 1.5, giving us 5.09 newtons meters, the torque unit. Here's a closing insight. This principle is the heart of all electric motors, because when you continuously flip the direction of the current at the right moments, you can keep your coil spinning. And that's what powers everything from your fans to your washing machine.